not maybe with the break in mind. We're a little rusty, so we'll go together. So we're given a line, which I don't necessarily love the format of that line. So if I rearrange it, I'll get, let's see, if I add the y over, that would make it a positive y equals, and then subtract the b over. That would be more to my liking, because what do I now know about the line? Slope of 6. The line is linear. That's always going to be true. The slope is 6, though. So if that line that has a slope of 6 is tangent to this graph, it would have to happen when b is equal to what? Okay. So this line being tangent to that function means that we need to find the place on this graph that has a slope of 6. So we need to find the derivative. So f prime of x is going to equal the limit as h approaches 0 for f of x plus h minus f of x all over h, which will be 3 and then x squared plus 2xh plus h squared minus 4 minus 3x squared plus 4 all over h. And what did I do? Bad, I forgot to bring down my limit. So when I get this all said and done, it'll be 3x squared plus 6xh plus 3h squared. The minus 4 and the plus 4 can cancel. Actually, the minus 3x squared and the plus 3x squared can cancel. I'll put this here just to be proper about it. All over h. And so my h's, both my terms in my numerator both have an h, which we're used to happening. So an h from each of those terms can cancel with the h in the denominator. And so now we're just looking for the limit of 6x plus 3h as h approaches 0. So if you plug in your h of 0, your limit is just 6x. So your derivative is just 6x. And even I'm getting annoyed with this long version. I would love to just use the shortcut. But your derivative is 6x. So your slope is at any given x value is given by the function 6x. We want to find where our slope is 6. Yes? So this will equal 6 when x is what? 1. So what is the point that our tangent line has to go through? 1 what? So here we have a quadratic that looks something like this. And it has a slope of 6 at 1 comma something. How do you find 1 comma what? Plug it in where? Right, to the function. Because this is the location on our function. So we need to know the point that's, yes, it's going to be on our function, but that point is also going to be on our tangent line, and knowing that point will allow us to find b. So we use the fact that this happens at an x value of 1 to find out that the y value at that point would be -1. Yes? So 1, -1 is the point of tangency. That's on the function, but also is on the tangent line. So knowing that 1, -1 is also on our tangent line, we're going to use that to find what b would have to be. So here's 6. So if you subtract 6 from both sides, we get -7 equals -b. So b would have to equal 7. So it's an application of using the derivative that's kind of tough to navigate through, wrapping your head around what we had to do right there. Any questions on that? Okay. The next exercise asks us for what value of x in the interval from -1 to 3 does the instantaneous rate of change of f of x equal the average rate of change. So first of all, what is the average rate of change? On this function, starting at -1, ending at 3, we first need to find what is our average rate of change. We want our average rate of change to equal our instantaneous rate of change. So the average rate of change is an algebra 2 problem. We find the coordinate at -1. -1, what would it be? Nope. Nope. 5. -1 squared is 1. Minus 4 times -1 is +4, so 1 plus 4 is 5. So there's the point on our curve at -1. The point on our curve at 3 is what? -3. So with those 2 points, I can find our average rate of change. y2 minus y1, average slope equals -3 minus 5 over 3 minus -1. It's going to be -8 over 4, which is -2. So my average rate of change is -2. I'm trying to find where the instantaneous rate of change also equals -2. Instantaneous rate of change should scream derivative. Okay? Derivatives give you the instantaneous rate of change. So to find my derivative, limit as h approaches 0, f of x plus h looks like that, minus f of x all over h do all your distributing. And you're canceling. X squared minus x squared is gone. Minus 4x plus 4x is gone. All of my terms have an h in them, so I can cross out one h from each of these up top and lose my h in the denominator. So it ends up just being 2x plus h minus 4. And so my derivative formula is just when I plug in an h of 0, is just going to be 2x minus 4. So we're looking for when does that derivative equal -2? When does that instantaneous rate of change equal what we had already found the average rate of change to be? So if I set that equal to -2 and solve, I get 1. So for what value of x in that interval? Is that in that interval? Yes. So with this kind of extension of the derivative, it's all, you're still finding the derivative, but then it's just kind of changing up what it's asking you to do and kind of working on the overall understanding here. This next one gives us a table of values for a function. And it wants you to then figure out an approximate value for f prime of 1. So in other words, what is the slope approximately at 1? How would you go about approximating this? How about this? I'll give you 2 minutes to come up with an answer, and then I'll give out a bonus point. Ready, go. I'm going to put this bonus point in term 3, by the way. whoever is so lucky enough to get it. Alyssa, what do you think? Or the answer. So like the slope formula between what 2 points? So the slope between those 2 points would give you 0.725 minus 0.707 over 1.02 minus 1. So that would be 0.18 over 0.02, which would be 9.9. Wait. It's 0.018. 0.9. And then that would be your answer? No? Zach, do you have anything to add to that? Winter? Jack? Anybody? Raise your hand if you have something to add to that, and I'll see who I get to first. Wait, Liam, what were you saying? Good. I like it. I'm going to give you a point for that, too. I'm going to give you a point, too, Alyssa. You both done. So this is obviously the slope beyond 1, coming out of 1. And I think Liam's right. It's wise to look at the slope going into 1 as well. So between these two, and if you do that, 0.707 minus 0.689 over 1 minus 0.98, you're going to get the same thing. Same thing coming in, same thing coming out. So it would stand to reason that a 0.9 is overall a good estimate, right? If you had noticed that, and if you had raised your hand and spoken up, I would have considered it. Did you check all of them? Are they all increasing by 0.18? Okay. So if you realize that it's a line, of course, whatever the slope is anywhere is going to be the slope throughout the entire thing. So that would work as well. I probably shouldn't have given you something that was linear because to kind of build this, just let's pretend that going into 1, so from 0.98 to 1, if the slope was 0.8 going into it, and the slope was 0.9 coming out of it, then 0.85 would have probably been a good estimate. At least the best estimate that we could come up with to our knowledge. But this being a line, obviously you get 0.9 no matter where you calculate it. Oh, so it's not a perfect line. But in this little stretch, it appears to be. Okay. So just using a table. And also just one thing not to make a mistake on is they're not asking you for f of 1, obviously. So you're not just going to say 0.707. They're asking you for the slope at 1, which is obviously a different thought process. And the last one here, they're giving us a point, f of negative 2 equals 1. Then they're telling us that the slope at negative 2 is 5. If the tangent line to the graph of the function f at x equals negative 2 is used to approximate the value of the 0 of function f, then that approximation is, okay, sketch a graph. You have some function. There is definitely a point at negative 2, 1. So my function has to go through that point. More specifically, at that point, at negative 2, we have a slope of 5. So that's a pretty steep slope, right? So my function does something, but is my function increasing or decreasing through that point? If the slope there is 5. Definitely increasing, and increasing pretty significantly. So I'm going to do something like this. And then who cares what happens afterwards? I really don't know. A gazillion different things could happen. But right at the point negative 2, 1, the slope is pretty strongly positive. So they're saying if this tangent line to the graph of the function, the one that I happen to sketch, at x equals negative 2 is used to approximate the value of the 0 of function f, meaning whatever the 0 is of your tangent line, which is here, is going to be pretty close to the 0 of your graph as well. Do you follow that? Can you see that? That the 0 of the tangent line is pretty darn close to the 0 of your function? The reason they're so close is because the point negative 2, 1 is so close to the x-axis. Obviously, the closer your point is to the x-axis, the closer those two roots will be to each other. But at any rate, how can we find the 0 of the tangent line? How would you find what that 0 is? Can you write the equation of the tangent line? Yes, because you have a point, negative 2, 1 is your point, and your slope is 5. So we can write the equation of the tangent line, y minus 1 equals m, x minus negative 2 will be x plus 2. So y equals, it would be 5x plus 10, but then I'm going to add 1 over, so it's going to be 5x plus 11. So there's my tangent line equation. How do you find the x-intercept of that, or the root of that? You find the x-intercept by setting y equal to 0. So if I set y equal to 0 and solve for x, divide both sides by 5, and I get negative 2.2. So the approximate root of our function is whatever the root of the tangent line is, negative 2.2. Just looking at the graph, is the root of our function probably greater than or less than negative 2.2? Slightly greater, right? But not negative 2. It's definitely not negative 2. We know that, right? So it's somewhere between negative 2 and negative 2.2. This is called linear approximation. It's how you can approximate the root of a function based on the root of a tangent line that's fairly close, has a point of tangency fairly close to the x-axis. So that's the idea behind that. So again, all of these applications of the derivative that are a little bit odd and word things differently. So you're going to have a little packet for homework that I'll let you start on right now. These numbers from the packet, 2, 8, 18, and 20, we just did. So you don't have to redo those. Those were multiple choice questions that we just did was long enough, huh? Now the truth comes out.